The only thing that it doesn't work.
Okay, let's have a quick look at this.
So I did it right.
All right, so let's quick close, get everybody involved in this a little bit. We'll all contribute to the discussion. What are we doing here? We got this function. Is that a rational function?
No, sir.
It is not. You're right. It's not a rational function. Find the following. Evaluate the limit of f of x as x approaches infinity and as it approaches negative infinity. And then identify the horizontal asymptotes. Okay, good. Find the vertical asymptote. For the vertical asymptote x equals a, evaluate the limit as we approach a from the left and from the right. Okay, this is, why are we doing this stuff? Because this is really valuable. What this is, we're going to come back and we're going to take a little break from this for a while, and we're going to, once we wrap up this unit, which is coming really soon, we're going to jump into our real calculus. We're going to jump into differentiation. Learn how to take derivatives and what they mean, and then look at applications of derivatives. But near the end of that, near the end of kind of the first portion of the class, when we wrap up our look at differential calculus, for now, you'll come back to it in college and do lots of other things with it too. But one of the big things we do in a first year calculus class like this is we're going to look at functional analysis using calculus. And so one of the big things we're going to do is I'm going to give you some function, and I'm going to teach you how to use a tabular method for just storing information about the important features on that function. It's, it's stuff that you'd use in the real world when you're actually trying to evaluate an economic function or a biological function within some kind of an application. But one of the things we want to do is we always want to know what's kind of the skeleton or the bones of the function, and those are the asymptotes. They tell us, as probably almost more than anything else, about what this function is going to do. If we can draw in what the horizontal and vertical asymptotes are going to be, then we can do an awful lot with that. And I want to go one step further with this also. Then I want to kind of retrace our steps a little bit. I don't know if I'm going to do it today. I think I'll go back. I don't want to interrupt the flow, but I'm going to wrap up a couple loose ends at the end. Did you guys talk about slant asymptotes? Like I always have. You did last year. You did.
Yeah,
Okay, so I want to review slant asymptotes too. And I don't think I gave you any questions related to that on the assignment. But at the very end, kind of when we're reviewing, I want to go back and introduce just one other little issue, which is slant asymptotes. Not a big deal, but there's some really good review in that. First of all, it forces you to review how to do division of polynomials, synthetic division, and long division of polynomials, which are both really big items in that. So probably haven't done a lot of that over the summer, I'm guessing, right? So we might want to review that a little bit. But we'll get there when we get there. So what about this one? This is not a rational function. How are we going to deal with the limits at infinity? There. Right, we've got this weird, this is one that, to do this by the book, so to speak, would be kind of a hard problem to do. But we can finesse our way through this. If you think back to what we know about the behavior of polynomials at the tails of the function as the function approaches positive or negative infinity, right? And look what's inside that radical on the top. Inside the radical is a polynomial, right? As we approach negative infinity or positive infinity, describe what's going to happen to that polynomial. Which terms end up being insignificant and which term becomes dominant? Yeah, the leading term is the dominant function as x gets really big in the positive or negative direction, right? And so when we're taking a limit of this function, the limit of f of x, that's equal to the limit of what much easier function at plus or minus infinity? Square root of 9x squared would be all, because this is, that's a constant, right? Mm-hmm. So the only part of the top function that's going to remain, everything else is just going to disappear into the background noise, and this is the only part that's going to be significant when we go to positive or negative infinity. And on the bottom, it's just going to be the x, right? Mm-hmm. So we end up with the limit of square root of 9x squared over x. as x approaches plus or minus infinity. So let's simplify. What is the square root of 9x squared? 3 times absolute value of x, right? Not 3x, 3 times the absolute value of x. So we get limit of 3 absolute value of x over x as x approaches plus or minus infinity. And if you want to, this is kind of optional, but remember, we could take that constant 3, and the limit is only acting on x's, right? We're taking the limit as x does something. So x is the variable of the limit, so to speak, right? The 3 is a constant. We could just factor that out in front, pull it out in front of the whole thing if you want to. You don't necessarily have to see the behavior, but it might be useful to write this as 3 times the limit of the absolute value of x over x as x approaches plus or minus infinity. And what did that look like? We looked at that function a couple times. It ends up being a piecewise function, right?
Yeah.
What's it do? I mean, just think about the behavior of the absolute value of x. The absolute value of x is either what or what? It's when x is positive, what's the absolute value of x? X, yeah, right. And what's x over x? 1, right? And if x is negative, the absolute value of x equals negative x, right? So then I'd have a negative x over x, which is negative 1. So remember, that was that function, that was that. It was pretty boring. It was just, you know, it was like one step. You have these infinite horizontal lines, and there's this one step in the middle where you jump from negative 1 to positive 1 at x equals 0, where you make the transition from positive to negative. Remember that?
Yeah.
So what's this look like then? Well, if I multiply by 3, if I multiply any function by 3, what am I doing to the function? What's that do to the, go back to algebra 2 and think about transformations. Yeah, vertical stretch. Yeah, we just stretch everything by 3. So instead of the function being, instead of the function, you know, doing this and negative 1 and positive 1, it's being stretched by 3. So it's just going to be at positive 3 and negative 3, right? Does that make sense? Okay. But, you know, do we really even have to mess with that? Well, I mean, not really. Arguably, we could just say if we take each of these limits individually, let's do that. Let's take the limit of 3 times the absolute value of x over x as x approaches positive infinity. Well, as x approaches positive infinity, what is the absolute value of x? At x, right? So that just looks like the limit of 3 times x over x, which is 1. So it's 3. Okay. How about the limit of 3 absolute value of x over x as x approaches negative infinity? Well, you already told me that's going to be 3 times negative x over x, which just becomes, that should be a limit. So I get negative 3, right? So that's my horizontal asymptote to the right, and that's my horizontal asymptote to the left. Okay? Make sense? Okay? All right, what about, so that's helpful. If we were to graph this thing then, we know this much. We know we've got this horizontal asymptote there and that horizontal asymptote there. Okay? That the function's ultimately going to stick to out of the tails. What about the vertical asymptote? That's a little bit easier to deal with. What are the zeros of the denominator? Only one of them. It's x equals 1. Okay? So if x equals 1 is a 0 of the denominator, then one of two things has to happen at x equals 1. What are the two possibilities? A whole is a possibility, or A vertical asymptote. How do we know which one's happening? What would cause it to be a hole? If it's 0 over 0. So if x equals 1 is a 0 of the top, then it's a hole. End of story. If x equals 1 is not a 0 of the top, it's a vertical asymptote, right? Then I get a number over 0. So all we have to do is just evaluate the numerator at 1. And what do we get? 9 plus 7 is 16. So I get the square root of 16 is 4 minus 4 is 0. What is it? It's a hole. There is no vertical asymptote. Okay? Make sense? Okay. And so what do we know about this function? Well, that doesn't help us a ton. It just tells us that there is a hole at 1 in our function. So somewhere out here at 1, we don't know what's going on in the middle. You know, when we do more calculus, we'll have a better idea how to fill in that blank. I mean, that's where we can take advantage of all the other stuff we're going to learn. So this is just still a great big question mark. But at least we know what's happening at the tails. We don't know what's happening in the middle, but somehow out here at the edges, this thing is going to, you know, it might be coming from the bottom, it might be coming from the top, but we know it's going to do that kind of thing out here at the ends, right? It's going to be asymptotic. Okay, make sense? Okay, good. Other questions on that? How about other assignments? Anything else you weren't sure about? What's after that one? That's the continuity stuff.
There's
I don't know, we just have the cons. Do we have another one?
Aren't there 2 continuity assignments?
Yeah,
there are 2 new? I'm on 1.3 PR2 content.
yeah, that's what
When are you gonna make the best of this?
Next week, like end of next week.
Like, right here.
I'm going to be.
Yeah, so there's 2. There's the first continuity assignment was mostly just about concepts, right? There wasn't as much math. Second one, there's some math where you're finding, as I recall, you're finding, you're writing intervals of continuity, things like that. Do you want to look at an example of one of those? And maybe not, that's fine.
I'll take any example.
Okay. I'll put up the assignment, and you just tell me if there's something here that looks like it's worthy of taking a look at. So. So the first questions I think were just about removable versus non-removable. Probably not a big deal by looking at those graphs. But when you don't have a graph, how would you know here? Well, you tell. I won't force you to. You just tell me when you get to one you want to look at. There's number 2.
For
This is practice 2.
Okay.
Yeah. Which one were you looking at?
I thought you said you guys were done.
Okay, the question on determining intervals where it's continuous. Questions on that? Well, what's the answer to that one? Right away. How come? You're right. Yeah, it's a polynomial, right? Polynomials are continuous everywhere in their domain, right? Okay, which is all real numbers. Okay, determine the intervals where that rational function is continuous. Remember that rational functions are also continuous every place in their domains, but there might be some numbers that have to get excluded because we're dividing by 0, right? Okay. Intervals of continuity. I'll tell you what, this is kind of a good one. This isn't a bad one. Let's just do this one. Hear me on this one, and then I won't force you to do any more of these if you don't want to. But there we go. I liked this one. I thought this was a pretty good problem.
Oh, okay.
So intervals of continuity.
question are you on?
This is like number 4, I think, or 5, something like that, 5. Is that what it was, 5?
Yeah.
So what are the intervals of continuity on this? Somebody give me one here.
0 to 1. Yeah, 0
Okay,
to
so but how am I gonna, so if I'm writing this with interval notation,
1. Bracket.
you're right, I get 0 to 1, but I'm using
Bracket.
Bracket.
And
bracket,
then parentheses.
parentheses,
And then
okay?
parentheses.
And then they use unions, don't they?
They
Commas
use
are-
commas.
They use
commas,
commas.
okay.
Then 1 to 2 with parentheses.
Okay. 1 to 2 with parentheses,
And then
okay,
2 to 4 parentheses, then bracket.
good.
And then 4 to 6 parentheses, then bracket.
Okay. We get that? Yeah, he's good, he's got this. All right. Same kind of deal. Okay, continuity checklist, remember these? So these are the ones where you're just looking at the 3 criteria, right? To see, you know, is the function defined? Is the limit defined? Does the does the value of the function equal the value of the limit? You're just going through the checklist. Which, you know, is it continuous? If not, which criteria does it fail? Okay, we did one like this yesterday. So I think you're probably good on that. Question?
Can you, show to do number 1?
On which
On
one?
this 1.32, the continuity.
Yeah. What about this guy? Is the discontinuity at x equals -3 removable? Okay.
Oh, yours are different.
Yeah.
Oh, it's different?
We were just talking about, so there's like certain ones where you can't see, so like there's like 2 lines, and then it goes off the graph and you can't see what is at the top.
Oh, okay, so that's an asymptote.
It's just an asymptote.
That means an asymptote.
Oh, okay.
Yeah, yeah, does that help?
Yeah, we just didn't-
Okay. Okay. Okay, what about something like this? Let's maybe give ourselves a little hint on this. Use the continuity of the absolute value function, absolute value of x. To determine the intervals on which the function is continuous.
Let me finish the question.
Okay, there's something, this is a little bit subtle here. There's something going on this one that's worth taking a look at.
You're on
Reveal
10?
the secrets.
Alright.
There's secrets going on.
You start on my question. And then
Okay, can you find any place, like, how do we analyze this? Where is this function discontinuous? Where is it continuous? Where is it discontinuous? What are some things we have to be aware of here?
that's 8 and negative.
First of all, I mean, we gotta know what's the domain of the function, I guess, right?
Yeah.
Yeah.
Okay. So, what is the domain of the function? What values of x can I plug in? Well, what's one immediate red flag we see that we gotta deal with? The square root, yeah. So we know we've got a square root, so everything inside the radical, which is just an x, has to be non-negative, right? So we know that x has to be greater than or equal to 0. That's one thing that has to be true. What else? Okay, there's something else going on there too. I've got an x in the denominator also, right? And so whatever's in the denominator cannot equal 0, right? So now we got another issue, another red flag's popping up. This is a blue flag, I guess. Another issue is that the square root of x minus 8 cannot equal 0, right? So let's combine those two things first of all. Well, that's pretty straightforward, but how do I solve for x here? Add the 8, okay? If I add the 8, I end up with the square root of x cannot equal 8. Cannot equal 2 just works just like equals. Now, how do I solve a radical equation?
Square.
Square both sides. Okay, but if I square both sides, you gotta be careful with this. If I square both sides, I might introduce extraneous solutions. So I end up with x equals 64, okay? So if I plug that back in, does it work? Square root of 64 is 8. Yeah, it does work, doesn't it?
Yes.
Okay, so x cannot equal 64 is one solution. Okay, x has to be greater than or equal to 0. Okay. Okay. So that's our domain. X is greater than or equal to 0. Is greater than or equal to 0, but x cannot equal 64. We could write it in interval notation if we wanted to. Okay, now what else happens with absolute value functions? Remember we had the absolute value of, well, never mind. I'll be saying something else about it. So where is this thing going to be discontinuous then?
64.
Okay, so it's going to be discontinuous at 64, and it's going to have continuity from the right at 0.
Yes.
Okay, that make sense?
Yes.
Okay. All right.
So then how would we answer that? The function is continuous on...
So what intervals? Let's turn it into intervals then.
Oh, so it's just asking for the interval notation of that? Okay.
Yeah, does that make sense?
Yeah, yeah.
Okay. All right, see if there's anything else. So it's gonna look something like that. Landon, see how that?
Yeah.
Okay.
Yeah. Hey, that's exactly what Christian had.
Okay. I think what number is this? This is 11. This one's only, these are kind of bonus problems. I'm not going to help you with these. You're only worth a couple points apiece on the last two. You got to kind of think about those ones a little bit. I might give you, if we have time, I'm going to do another problem that might help with that if we have time. All right, so click and closed. I want to show you, I want to at least start the discussion on something else then today. So what I want to look at today, this is a really cool, it's a cool theorem. It's not very hard to apply, but this is your first calculus theorem, really, that you have to kind of wrap your head around a little bit. It's called the intermediate value theorem. And you're going to tell me what it is. It's not very hard. It's just logical. So if I have some function that is continuous on the closed interval from A to B, okay, so we'll call this A and that B, and it's continuous on that closed interval, then what could you tell me about the existence of a place on the function where if the function has a certain value at A, so when I evaluate the function at A, I get the ordered pair A, f of A. And when I evaluate the function at B, I get some other value, let's say B, f of B. What if I pick any value that's between f of A and f of B? Okay, I'm going to call that value C, or f of C. Now I won't call it C. I won't call it anything for now. I'm gonna pick some value between f of A and f of B. So those are the y values at A and the y values at B. Can you tell me something significant about that? Think about our definition, our graphical definition of continuity. A function is continuous if I can graph the function without picking my pen off the board. So here's f of A in this example. Here's f of B. We'll pick some value in between. Let's pick that value, who knows? Can you tell me something significant about that? It exists, yeah, what else?
Just like the limit from the left and the right approach the same value.
True, true. And nothing even that complex.
Has to cross it.
Has to cross it. That's it. The function has to have that value at some place in between A and B, right? Does that make sense? There's no way you could graph this thing, a function, right, that's continuous. Now, if I had some kind of crazy function where I could have gaps in the function, well, then all bets are off. But if it's a function that is continuous, I absolutely have to have that y value at least once during the interval. Pretty straight, I mean, it's obvious, right? And I don't care what happens out here, I'm only looking between A and B, but in this case right here, it happens right there, right? So the intermediate value theorem guarantees there's going to be the existence of at least one value of x between A and B. So that's on the open interval from A to B, at least one value where the function has this intermediate value that we select, whatever it is, okay? So here's the language, you know, one manifestation of the language in this textbook. It all essentially says the same thing. Let f be continuous over a closed interval from A to B. If z is any real number between f of A and f of B, then there is a number c, at least one, could be many of them, in this. That's actually incorrect. It should be like that. In the open interval, satisfying f of c equals z. Okay? Right? So doesn't it make sense? I mean, here's f of A, here's f of B. If z is in between, the function has to go through it once, and it might go through, if I draw a different function, it might go through a whole bunch of times, right? But at least once, okay? This is what we call, so there's a number c on the interior interval, and the open interval, that satisfies f of c equals z, okay? This is what we call an existence theorem in calculus, or just in math. It doesn't really do anything for us. It just guarantees the existence of something that then we can go look for using algebra. But at least we know whether it's worth looking for, right? If we know that something exists, then at least we don't have to worry about wasting our time, I guess, right? So let's take an example. Here's the language out of your textbook. Is that right? Is it the closed interval? It says it here too. I'm going to investigate that, but it has to be the open interval. It has to be. And you prove it to me. Why, you see my issue with this? Why, I think those should be parentheses. And it's possible I'm wrong about this, but I don't think so.
If you don't exist between those 2 points, can't your middle point just be one of those points?
Okay, but if it's a function, points can't line up vertically, right?
Yes.
You see what I'm saying?
Yes.
So if, and you guys fact check me on this. So if there's f of A and there's f of B, right?
Yeah.
And z, or whatever you want to call it, they call it f of c equals k in this case. In the last textbook, they called it z. If z is between f of A and f of B, right? And you're defining between, okay, and you're defining between as not being equal to. I guess there's the crux of the issue.
Yeah.
If f of A and f of B are equal, I guess you could say between. And this stuff comes up all the time in math. You'd be amazed how frequently you'd think math would all be cut and dried, right? Like there's a black and white answer. Not at all. There are things that'll come up throughout the year where there's still like vigorous discussion about this among mathematicians, and some of them will say, no, I think it's this way. Others will say, no, it's that way. And there's no resolution to it, you know. The idea of betweenness. Betweenness is a real word in math, and betweenness, does betweenness require that it's not equal to the values it's between, or could it be equal to the values? That's where this is, but if we assume, to me, betweenness means there have to be two different numbers, and we're picking a number somewhere in between those numbers. It's not equal to those numbers. It just seems to be consistent with the meaning of the word.
It would be like in between or equal to.
Yeah, so it's, if that's what we called z, let's say, there's that number that's halfway in between, or somewhere in between. Do you see then that the endpoints couldn't sit on z,
Correct.
right? And so there has to be some place in between a and b on this open interval where it's going to cross through that horizontal line. Okay? So I know we're splitting hairs here, but these are the kinds of things that mathematicians kind of argue about.
Z just be your endpoint though?
Say it again.
Couldn't Z just be your endpoint? Because you already know it goes through it.
Well, but if z is your endpoint, then is z in between f of a and f of b? Because z is the y value. We're looking for the values of c where this occurs. The intermediate value theorem guarantees there's at least one x value where the function passes through the intermediate y value, right? And so what I'm suggesting here, and this is, this is open for discussion, I would say that c cannot be at the endpoints. Because if it were, then that would mean that z was equal to f of a or f of b.
Yeah.
And the way I'm choosing to define betweenness doesn't allow that.
Also, that's not useful information, you already know.
Right. In a way, it's
Pointless.
right. It would be sort of redundant anyway. But you get the idea? But in both cases, they seem to indicate that you can include the endpoints. So I guess they're going to include the sort of the collapsed version of this where f of a and f of b are equal. Not sure why. But anyway, that's not important because we never look at any problems like that anyway, right? Let's look at some examples.
You tell me, Mr. Ryan.
So f of x equals, let's look at a value here. F of x equals x minus cosine x. We're going to show that that has at least one zero. Okay? Without doing any math, we can show that that has at least one zero. Anybody think of a way we might be able to do that? Show it has at least one zero using the intermediate value theorem. What's a zero? Where it crosses the x-axis. Okay, so where y equals, okay. How can we show that there's at least one value of x where y equals 0? Let's review the criteria for the intermediate value theorem. If we've got a continuous function, is this function
Yes.
continuous?
Yes.
It is, right? If we have a continuous function,
Oh, so can you prove that there's one above zero, one below zero?
What about that? Okay, if we could find a value of x that we could evaluate this function in, where the value, where f of a, let's call it, is negative, and f of b is positive, we proved it, didn't we?
Big brain.
Oh, yeah.
Right? That's it. So we just got to find a value and we're set.
2.
2. So we know at 2 it's going to be positive, don't we? Because what's the values of cosine are going to swing between what? 1 and negative 1, right? So we can guarantee there's one value we can pick. We can pick, for example, f of 2 is going to be 2 minus cosine 2. Well, I don't know what that is exactly, but I know that it's positive.
Yeah.
It's 2 minus something whose maximum value is 1. Okay? Find one that's negative.
Negative.
Yeah? Yeah, there you go. Right?
Big brain time over here.
f of negative 2 equals some negative number. We can plug it in a calculator and find out what it is. And if we want to pick something, like we could probably pick some convenient fraction of pi instead of 2, right? But we don't need to. There's no point. We know if this is positive and this is negative and the function is continuous, then it has to pass through 0 somewhere. Drop the pen, we're done, right?
Oh, you could have
By the intermediate value theorem, it guarantees that it's going to pass through the intermediate value of y equals 0, which means there's a 0. That's pretty cool. But you can do that, right? Almost no work done there, right? Just a little scratch in our head and we got an answer. Okay? So how about this? If f of x is continuous on the closed interval from 0 to 2, and f of 0 is positive, and f of 2 is positive, can we use the intermediate value theorem to conclude that f of x has no zeros on that, over that interval?
So,
Okay, so
Yeah.
we could sketch something out here to kind of illustrate what we're talking about. So at 0, the function is positive. F of 0 is positive. F of 2 is positive. Can we use the intermediate value theorem to conclude that f of x has no zeros?
could you do it like we did in the last one, over the x-axis? So then we know that it doesn't cross there.
Would it be, you don't have large enough sample size?
Say it again.
No, because you don't have large enough sample size, so you only have this section.
Right, but okay, but even, we're saying on this interval, from 0 to 2,
Yeah.
Oh, yeah.
Yeah.
has no zeros?
Mm-hmm.
Okay. You gotta be careful about that.
Maybe.
The converse of a theorem is not always necessarily true, right? Does it have to be true? All the intermediate value theorem says, you gotta be careful with this, all it says is that if there is an intermediate y value when the function is continuous, there must be at least one x value where the function passes through that intermediate value, right?
Because
Could be like-
it could dip,
Yeah.
go up.
Yeah, there's no reason, this function might do this, right? It might be going from here, it might be sweeping way down there and then going up through there, who knows,
Yeah.
right? Okay, so the intermediate value theorem cannot be used in that case. We absolutely don't know, we don't know what the function is, right? Make sense?
So do we say it can't be used?
It cannot be used,
Oh,
can't be used.
okay.
Because first of all, it doesn't even, the intermediate value theorem, you have to think about these existence theorems as we're just going down the list. Can we check off the criteria? What are the criteria? Is it continuous? There's two things. Is the function continuous? Well, it tells us it is. Check. But then the other thing is there a y value that's trapped between the two, the two f of a and f of b? And there's not. The function doesn't need to say anything about that, does it? Right?
Even if it did say there was a y value in between, can you still couldn't conclude that there's no zeros because it can still go down through. Even if it's like there's a y value in between the two that it passes. I don't know what I'm saying.
Yeah. Or you could pass through it and then go down.
Yeah.
Go down before.
Yeah.
Right. Right. I mean, this one has to go through all the, and in fact, it goes through every value between f of a and f of b, doesn't it? All infinite values it passes through. But it passes through potentially a bunch of other values too, like in this case. Okay? Just think about that one. Okay, how about this one? Can we use the intermediate value theorem? We can just calculus what's called IVT, right? To prove that f of x equals 1 over x has a 0 on the interval. Second order, isn't it? On the interval from -1 to 1. Okay, well, let's check it out. Yeah, so what's f of -1? What's f of 1? Well, 0's in between. So can we do it?
Yep.
No, how come?
Oh.
What are the criteria for the intermediate value
Oh,
theorem?
we
You have to meet those.
Can't divide by 0.
Okay, so what's going on? Once again,
It's
we
not
go back.
There's a
continuous.
hole at 0, dude.
Okay, yeah. here's here's the key language.
You can't do it like that.
If F is continuous on the closed interval, if it's not, doesn't apply. This only applies for continuous functions, right?
I trusted you.
So in this case, it's not continuous, it's discontinuous at 0, and so the answer is no, right?
Practice.
I did.
I'll
do that. I've tried to do that. I
Figure it
won't
out.
be, I'm not always successful.
Been bamboozled.
I got you beaten Boozled right there.
Wow.
Still be great.
All my trust.
Yeah, how about this one? What are we out of here? 1 minute?
Yeah.
Oh, never mind.
How could this happen to me?
Yeah, I'm gonna put the assignment up, but I'm gonna push the deadline back a little bit. It's, because we still gotta do some stuff. Yeah.
Can you say that there is a continuous line, but there's not, but there's